All right, so we're talking about our document generation. Okay, well, we have a model for document classification, right? Okay, and we said the words these are the words. They are generated based on a multinomial distribution with vector of probabilities theta. Okay, so come from this is multinomial distribution for the words. Okay, and which theta we use depends on the label. Okay, the label of the document. The document label. Okay, and the label itself is based on a coin flip. This is Bernoulli parameter theta. Okay, and this Bernoulli parameter itself comes from a beta distribution with hyperparameter gamma. And then the theta distribution over here comes from a Dirichlet distribution with hyperparameter gamma. Okay, and we have a plate to indicate this is the case for each document. We have n documents total. And then within the document, we are generating a bunch of words themselves. Okay, and we have a total of r sub j words. That's how many words are in the number of words. R sub j is the number of words in document j. So this is where we left off. Is that okay? And so this is kind of the graphic representation of our model. And if we want to just kind of say each of these things, we can say L sub j, this is the document label, comes from a Bernoulli, I guess Bernoulli has two L's, Bernoulli distribution with parameter pi, and pi itself comes from a beta distribution with gamma, vector gamma pi, right? Gamma pi 0 and gamma pi 1, but we'll make it a vector. Okay, and then the words, the bag of words that we have, W sub j, which is a vector, are drawn from the multinomial distribution, where we draw a total of this many words drawn with parameter vector theta. Okay, and maybe I will say theta sub L. Because there is a different theta sub Lj. Okay, so we have different theta vectors depending on the label L. Label L sub j. Okay, and then that vector theta itself comes from a Dirichlet distribution, which is similar to the beta with hyperparameter gamma. So this is kind of our representation of how we are generating our documents, which are represented as bags of words. And so what we want to do is we want to create a posterior distribution, which is going to estimate the label based on everything else. And in order to do that, we're going to have to do the joint distribution of everything divided by everything else, right? So what we're going for ultimately is to get okay, this is good. Can I flip to the next page here? Okay, so so we want to get to probability of the label given kind of the words that we see, the words in the document. I guess, and this will require the joint distribution of everything together. Okay, and so our joint distribution for all documents. Okay, so keep in mind that we've represented the corpus of documents. Okay, we've got kind of the corpus 0. This is kind of all documents labeled 0 put together. Okay, and then same thing going for kind of the corpus of documents labeled 1. Okay, and because we're treating these documents as bags of words, it's kind of just like dumping all of the bags together into one big bag that's labeled 0, and then all of the words in another bag that's labeled 1. Okay. Oops. So, so what we want is we're going to go for the total joint distribution of all of our documents together for the entire document collection, total joint distribution. So this is just going to be all of our letters together, okay? So it's going to be the probability of kind of the corpus of documents, the labels, the parameter pi, the distribution of words in label 0, the distribution of words in label 1, and these are based on hyperparameters. The notes use a semicolon, but I think a vertical bar is fine for given. These are based on the hyperparameters for pi and the hyperparameter for theta. Okay, so this is everything here. And what we're going to do is we're going to write this as a product. Okay, so this is kind of the joint distribution. We can rewrite this as a product, right? Product of probabilities. All right, and then kind of this is just a basic review of, this is kind of the review of your Stats 10 probability rule, right? Which is, we can say probability of A and B, or if I say A comma B, probability of A comma B, this is equal to the what? Probability of A times the probability of, what do we write? B given A, right? Okay, so basically this is what we're going for, and then so that's the general rule, and then if A and B are independent, then probability of A comma B is equal to the probability of A times the probability of B, right? Okay, so basically these are the two rules that we're going to use to just factor this whole thing apart. Okay, so we use these two rules and we say, okay, well, what's independent of each other and what's dependent on each other? Okay, so this entire thing is going to factor into. So we're going to start off with the coin flip parameter, pi. What does pi depend on? It depends on gamma sub pi, okay? And this is going to be a beta distribution, right? Okay. Then we can say, okay, well, what is the probability of the label? Okay, what does the label depend on? The distribution of the label comes from a Bernoulli distribution, right? And the Bernoulli distribution has parameter p, or in this case pi. Okay, so the Bernoulli, the label depends on. Okay, so here maybe I'll write all of these out. Okay, so this is the kind of the label probability pi. Label probability pi depends on parameters of beta, right? Parameters of the beta distribution, okay? This is the label depends on the label probability, pi, okay? Depends on the pi. Okay, what else we need? So we've accounted for the L. Let's account for the theta. So theta sub 0, the vector of probabilities defining our multinomial distribution, this depends on, this comes from what? The Dirichlet distribution. Okay, so this is the Dirichlet distribution for theta, and the probability for the vector for the multinomial labels in label 1 also depend on the Dirichlet distribution. Okay, what was that? Okay, so this is the vector of multinomial probabilities depend on the Dirichlet parameters. Okay, and these, you know, once we have the theta and the Dirichlet parameter, you know, based on the Dirichlet parameter, the labels are independent of the theta, right? So I don't have to worry about the label, whether the document is labeled 0, 1, if that depends on the probabilities of the words in label 1 or the probabilities of the words in label 2, right? As far as the model generating thing goes, these are independent. So these are being multiplied together because they are independent of each other. Okay, and then so finally, let's account for the documents themselves. So we've got the probability of kind of our corpus of documents labeled 0. This depends on, so all the words that we see depend on the vector of probabilities for the words and the vector of labels. And all of the words that we see that are labeled 1 depend on the vector of probability of words for label 1 and the vector of labels. That's okay? So this is all the words we see depend on the probabilities of those words which is theta, and the labels of the documents. L. Okay. So we've factored apart the total joint distribution into each of these things. Okay? And so we have, we have some conditional things, but, given certain things, some things are independent of each other, right? So, yes, the words that we see depend on the word probabilities and the labels, okay? But the word probabilities only depend on the hyperparameter. The word probabilities don't depend on other things, okay? And the label only depends on that value pi, and so on and so forth. So we're factoring apart our entire document as such, okay? All right, and so now we can start to take a look at each of these things and break them apart and start to think about how can we sample, start drawing samples for these things, okay? So, if we go out and we try to do, if we have a complicated model, Gibbs sampling is an appropriate thing, and it just requires us to do a little bit of thinking to then, factor something out. And I think, the first time you see this, it looks a little bit scary, but, if you kind of talk yourself through every single thing, what each of these things mean, I think it's rather reasonable to understand what we see here. Okay, so let's just look at each of these pieces. Okay, we've got the probability of pi based on gamma sub pi, which the vector gamma sub pi, which is going to be the probability of pi based on gamma pi 0 and gamma pi 1. And this is basically a beta distribution. Basically, this means pi comes from beta distribution with gamma pi 0 and gamma pi 1, okay? And the beta distribution has, we have basically a normalizing constant, which looks scary. I'll say scary normalizing constant, times, and it's just pi raised to the gamma pi 1 minus 1 times 1 minus pi to the gamma pi 0 minus 1. Okay, so we just have, so what we have is the probability, the PDF for pi given gamma pi 0 and gamma pi 1 is equal to some, we're just going to write some constant times pi raised to the gamma pi 1 minus 1 and 1 minus pi to the gamma pi 0 minus 1. Okay, or we can just say is proportional to all of this. All right, let's look at the Dirichlet vector. Okay, this comes from Dirichlet parameter here, and I'm going to just say this ends up being equal proportional to a Dirichlet distribution, which it ends up being, this is the product from I equals 1 to V, how many kind of the words that we have, and it's theta sub I raised to the gamma theta minus 1. Okay, so this is the PDF of it for the Dirichlet distribution. Yes.
Can you explain, I guess, the significance of the Dirichlet and what's like unique about it in this sense?
So yeah, the Dirichlet is a kind of like a multivariate generalization of the beta distribution. So, for a binomial distribution, kind of the conjugate prior is the beta, because the binomial distribution will produce, you'll have n total observations, and you'll have basically x yeses and n minus x no's, okay? And it's binomial because there's only two possibilities, and the probability of a yes is equal to the parameter pi. For a multinomial distribution, you're going to have n total observations, and you'll have x, I don't know how to label these, x sub 1 of category 1, x sub 2 of category 2, x sub 3 of category 3, etc., etc., and then x, basically n minus the sum of the other x's of the last category. Okay, and the probability of drawing from each category is defined by a vector theta. Okay, and likewise, for the binomial, we can say pi comes from a beta distribution, and beta basically goes from 0 to 1, and it has, some kind of shape, maybe like this or maybe like this, just some shape that goes from 0 to 1, saying that some of these values are more or less likely. Theta, if we have, is multidimensional. Let me see if I can find one here. So here is, this is a picture of kind of a three-dimensional Dirichlet distribution. Okay, so indicating, I don't know if you guys can see this. This is indicate. Let's find a better picture. Basically, what you're going to get is a vector of all of these. These make it more complicated than it needs to be. But basically, the draw from a Dirichlet, so draw from a beta is a single parameter between 0 and 1, indicating the probability of getting a yes. Okay? With a Dirichlet, you're going to get a probability of, a vector of probabilities that either add to 1 or can be normalized to add to 1, indicating the kind of the relative probabilities of getting category 1 versus category 2 versus category 3, and so on and so forth. And in our case, when we are doing modeling our document as a bag of words, we have to say, okay, well, how many different words are possible? And I don't know, maybe we say there's 80,000 possible words or something. Or maybe we just say, okay, we're going to use a easier vocabulary of only, 2,000 words or something. And then, based on that, we create our Dirichlet distribution will have to have basically a vector of 2,000 probabilities, okay, kind of showing the relative frequency of each of those words there, okay, and so that's the Dirichlet, and so all of this stuff looks more complicated than it needs to be, but let's find. So okay, here we go. So this is like, where did that picture go? I don't know if you guys can see this. Okay, so this would be all three values. So this kind of represents, you know, between 0 and 1. You know, you're going to get a value. You now have like three values. So our Dirichlet has 3 things, and it says, you know, like, everything has equal probability. This is the equivalent of the beta distribution that's uniform between 0 and 1. Okay, and then as you can imagine the beta where you only have 2 things, and you had 2, 2, then you get like a slight hill, and then as it goes 50, 50, you know, it gets more and more pointy. Same type of thing. So here when we have 10, 10, 10, it's saying, okay, we're expecting something in the middle where all 3 values are equally likely. Over here, we're saying one of the values is much more likely than the others. So a draw from a distribution like this would probably be something like 10% category 1, 80% category 2, 10% category 3, something like that. Okay? And this would be just kind of the opposite, where it says, okay, we're going to get 10% from category 1, 10% from category 2, and 80% from category 3. Or a random draw. So maybe another random draw would end up being like 9% category 1, 11%, or, you know, 9% category 1, 8% category 2, and then 83% category 3, or something like that. Okay, because they're still random draws from a distribution, but they tend to be centered around, you know, some certain thing there. Okay. Anyway, that's kind of the illustration here. All right. Dirichlet distribution. This generates the theta, which is the vector of all the probabilities over all the words that we might see. Okay. And now we're going to talk about the words themselves. Okay. So we want the probability of kind of the corpus of documents, okay? And basically, when we look at the corpus of documents, this is going to be just basically be pooling all of the words for documents labeled 0. Okay, and so if we just say, okay, well, let's talk about what about the words in one document, given its label and the vector according to that, you know, and the vector of word probabilities according to that label. Okay, this is going to be the product. The total probability of all of our data is a product of seeing that particular word this many times. Okay, so, you know, let's just say there were only 4 possible words, okay? Just for simplicity. So we'll say 4 possible words. And the words are apple, banana, cats, and dogs, okay? And perhaps our documents are either about animals or fruits, okay? And so if we'll say label equal to 0 means it's about fruit. Okay, and so we might have theta sub 0 is basically going to be a vector of 0, I don't know, maybe 0.45, 0.4, and then 0.1 and 0.05. Okay, so this is if our apple, banana, cats, and dogs, if our document's about fruit, we would expect apples and bananas to show up a lot more than the words cats and dogs, or something like that. Okay, this is really simple. And then if label is equal to 1, it's about animals. This is like the dumbest example, but I hope it illustrates what I'm talking about here. And we might say, okay, well, if it's about animals, we're going to see apples only a little bit, and maybe we'll see bananas a little bit more, and then we'll see lots of mentions of cats and lots of mentions of dogs, or something like this, okay? And thus, let's say your document, W sub n, your vector here, is basically how many times we see the word apple, banana, cats, and dogs, okay? And then so maybe we see the word apple 10 times, and the word banana 12 times, and the word cat 3 times, and the word dog 5 times. Okay, so this is apple, banana, cat, dog. Okay, and thus the probability of this data is going to be 0.45 raised to the 10, 0.4 raised to the 12, 0.1 raised to the 3, and 0.05 raised to the 5, something like that. Okay, and we can see that the probability of this data is much higher than if we used the other label, right? Probability of data if label is equal to 0, and we'll say probability of the data if label is equal to 1, this is going to be 0.05 raised to the 10 times 0.08 raised to the 12, 0.45 raised to the 3, and 0.42 raised to the 5. Okay, and we can see this is going to be much more likely, and thus if we see words like this, we would come to the conclusion that okay, this document is about fruit, type of thing. Okay, does that kind of make sense? Yes.
I just saw that you said W, so you said like probability of the data no, it's equal to 0, it's just the probability of what's the totality of each W. So are we just using the same W for probability data L is equal to 1? Or can you explain W for
Okay, so here this is the probability of what we observed in our document, right? So probability of what we observed in our document which is W sub n, a vector W sub n, given the label and vector of probabilities for words. Okay, and so basically this is over here, this is the probability of this document, which is 10 apple shows up 10 times, banana shows up 12 times, cat shows up 3 times, and dog shows up 5 times. It's the probability of getting that document if we have the label 0, and the vector for 0 is this. Okay, so this is, I don't know where I fit this, but this is probability of W sub n, which is what we have here, given label equals 0 and theta 0 is equal to kind of the vector, 0.45, 0.4, 0.1 and 0.05. Okay, if that's what we have here. And over here, this is the probability of my document W sub n given label is equal to 1 and the vector of words for label 1 is 0.05, 0.08, 0.45, and 0.42. Yeah. So I'm just saying, if somebody asked you what's the probability of getting this thing, we would say, oh, okay, we would do it this way. And this is just a silly example where we're pretending our language only has 4 words in it and there's only 2 subjects. But we can imagine just expanding this over a bunch of words. Okay, but the same concept holds the same. Okay, so this was the probability for one document, and basically all we have to do now is we just say, okay, now we take the probabilities of the words in a document, and we're going to multiply them, and we're going to say each document is independent of each other, and so thus the total probability of the entire corpus, okay, is the entire corpus of documents. If I take this, so this is the probability for one document. And so now the probability of all the documents will be the corpus of label X given L, and the theta for that thing is going to be basically the product of all of these things. So I have the product of theta sub x sub I raised to the W sub n sub I from I equals 1 to V, and then this is for all, basically all documents in the corpus. Okay, and then so this product just ends up being the product for all of our words, and this is x comma I for the raised to the natural count of I. Okay, so basically it's just is the count of word I across all documents and with that label. Okay, so if one document, what was it, the previous one, 10, 12, 3, and 5, okay, 10, 12, 3, and 5, and then we have, another document, so this is document 1, okay, and then we had, document 2, document 1 has L equal to 0, and document 2 also has L equal to 0, and then maybe it has 8 and 13 and 1 and 2, something like this. Basically for the total documents, and if this is our entire corpus, our corpus for 0 is basically 18 times we saw the word apple, 25 times we saw the word banana, 4 times we saw the word cat, and 7 times we saw the word dog. Okay, and then this is kind of like our natural counts here. Natural counts for label 0. That's what we have. Okay, does that kind of make sense? And so this is how we're going to evaluate this quantity. How we evaluate probability of C sub x given L theta sub x, right? And so we said this is what we've got, right? Because again, don't lose sight of the big picture. Is at the beginning we wanted to be able to express this total joint probability, and we broke that down into each of these things. And now we have an equation for each of these parts. We have an equation for this. This is the beta distribution. This is just a Bernoulli. This is a Dirichlet, and this is the kind of the multinomial all combined together. So now we have equations for each of these pieces. Okay, and so now that, whoops, where did we go? Okay, so now that we have equations for each of these pieces, then we can start talking about sampling from each of these. Okay, and shoot. Okay, I'm gonna skip over. Okay, so anyway, do your reading and make sure you understand as you're going through. And I'm hoping with my commentary, and there's actually very good explanation in here. You know, slow down and make sure you understand each equation. Okay, don't just say, it looks like math, I'm gonna skip it. You know, make sure you understand each equation. I think everything is reasonable, and then I'm gonna skip out. When we get back to Monday, I'm going to skip to section 2.5. I didn't get to cover 2.4.2 and 2.4.3, which talks about the choice of priors and integrating out pi, which is worth worth checking out. But I think you can read through it, and you know, it looks intimidating because especially the integrating out pi, they have integrals where they integrate out the thing. But it's basically, let me just talk about this concept of integrating something out. Let's say we have a joint distribution between A and B, okay? And value B can take on the value, variable B can take on the value 0, 1, 2, and 3, okay? And variable A, let's say, can take on the values 0, 0.5, and 1. All right, and then so you have some kind of distribution, a joint distribution here, okay? And I don't know, maybe we have 0.05, 0.06, 0.0. How many things do we have here? Okay. All right, I'm just gonna keep just doing all of these things. I think these are all pretty small. And then the last one, I don't know, what's 5 through 15 summed up? 15 times 7 is 70. I don't know. What is it? What's 5? Sum 5 through 15? What is that? Why aren't you starting right now? Okay. Well, anyway, everything left over goes right there. Okay. And then and basically, when we're talking about integrating out a thing, so right now we have the joint distribution of A and B. But if we just want to go down to the distribution of B, what we do is we sum up the probability of A and B, but we sum it across all A's. Okay, so we find this, and all this is doing 0.05 plus 0.09 plus 0.13, which is 14.27. Is that right? Okay, and then we do this 6, 10, and this is 0.30, and this is oh shoot. Okay, well everything we have a problem because this actually goes over. Oh no. Yeah, it goes over 1. Okay, so anyway. But anyway, here we'll get rid of these ones, and then I think then this has to be if we have 0.27 and 0.3, then I have 0.33 left over, 0.18, so this has to be 0.15. Oh, that works out. Is that right? Okay. No. 7. No, I don't know what I did. Okay. Well, anyway, it has to add up to 1, right? Okay. So the distribution of B is basically you're summing up the joint probabilities across all A's, okay? And then it just generalizes to for continuous, okay? The probability of B just becomes the integral of probability A and B across all A's, okay? And this is what they're trying to do. They're trying to get rid of the pi. Okay, they're trying to get the value by integrating out. We integrate out a in this case, and that's just to get the marginal distribution of one of these things based on the joint distribution. Okay, so anyway, check that out, and we'll see you guys on Monday.